Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a material nonlinear analysis using salome. I have taken a simple geometry of dog moon shape. One side I am just fixing it, other side I am just pulling it in with a force of 1 for 5 Newton. The area is here 0.000036. That is to apply the force in Aster. I have taken this area. And within the elastic limit, I have taken the Young's modulus of 210 gigapascal and Poisson ratio is 0.3. Then after that, I have taken a stress strain curve. So this is the stress strain data I have taken. So this y-axis is strain and x-axis is y-axis is stress and x-axis is strain, and the strain, the x-axis should not be 0 and it should be in the increasing manner. That is the only way we have to apply in Aster. So now we'll solve this problem using salome. I have opened salome here. First we will import geometry here. First go to geometry model. First go to file, import step file. I have saved it as a step file. So this is my file. I just opening here. So take into account the unit millimeter embedded into the file. Yes, I just want to take the same unit. Now just fit screen. The same millimeter is converted into a meter here. You can see it here. Just select this file. Go to inspection, dimension, bounding box. Now it is in meter. So just close it. So if any file you are importing into this geometry model, you are designed in some other software and you are importing into this salome, you have to check the dimensions, what dimension it is came here. Then after that, we have to continue with that. So I have imported here. Now we'll create a groups to apply the boundary conditions. So left side I just want to fix it. Select this face, add. I'm just naming as fix. Just apply. Right side I just want to apply the force. Just select the add. I'm just naming it as force. Just apply and close. Now I have created two groups to apply the boundary condition. Now we can save this file. Just Ctrl S. It is navigating into the same folder. Just save it. Now we'll go for a meshing model to create the mesh. Go to mesh model. Select this file, mesh, create mesh. Here you just go to NetGen 1D, 2D, 3D algorithm. NetGen simple parameter. Instead of number of segments, go for local length 0.001. I'm just giving. Just say OK, apply and close. Right click this one and compute it. This mesh is enough. If you want to make little finer, you can reduce the local length size. Then you will get little finer. I hope this is fine. This mesh is okay for me. So now we'll check the groups also. So we have got the same groups, whatever groups we have created in the geometry, that also came here. Now we can go for Aster study to create the setup. I'm just saving this file. Just go to Aster study. Just say OK. Now we'll add the command one by one. First I'm adding stage. First we have to read the mesh. First read the mesh. Choose the mesh one. MED format. Just apply. Just apply and OK. Now we have read the mesh. Then we can go for model definition. We have to define the model. Choose assign finite element. Here finite element. Edit. Everywhere. This is not the thermic and acoustic analysis. We have to choose mechanic and 3D model. Just say OK, apply and OK. Then we have to define the material. So here we have to define the traction curve. This traction curve into the material property. So for that we have to define this function. So just go to functions and list, define function, and just naming this as a stress strain curve. Stress strain. Here coordinate. So this parameter whatever we are choosing, this is the x coordinate. So I just want to define x coordinate as strain. So EPSI is the strain. Just go to edit. Here you can see this one is the x coordinate value. This is the y coordinate value. So we can type one by one also. See here 0.001 2e power 8. So here we can type it also 0.001 2e power 8. By adding one by one we can do. This will take much time. So instead of that we can directly import the file. So here I have the Excel data. So this is my stress strain data. First one is the strain, second y-axis is the stress. I have plotted like this. So same data we can directly import by using as .csv file format. So I simply just copy this data and paste it in the new sheet. Then you just go to file, save a copy. Here just choose the into CSV format and save it as a stress strain CSV. I just save it. I have already saved it. So just save it here. So the same file we can import it here. Just use this import data table, fixtures, code Aster. So 71. Just select this file. Just save OK. Now you can see it here. We got this stress strain data here. Now we just simply select it and plot it. So this is the data we got. So now just simply OK. Here we have to define the interpolation also. So ratio name, this is, we can change it. Any name we can give it, is no issue. The first one is only the primary parameter we have to define. X coordinate parameter if epsilon, that means strain we have defined. The remaining y coordinate it will automatically set as a stress. So then interpolation, this is actually a linear interpolation, and right side extension and left side extension. So in stress strain curve you can see it here. Right side there is no extension actually. It has to be excluded. Then left side excluded, and right side we can extend like this. So it's a linear. So that functions we can define here. So right side is a linear extension. Left side is excluded. There is no extension. So just say apply and OK. Now I have defined the stress strain curve. Then we can define the material. Just go to define material. Here I can name it as steel. Isotropic. Within the elastic limit we have to define Young's modulus and Poisson ratio. Just edit. This Young's modulus is, here you can see 210 gigapascal and Poisson ratio is 0.3. 210 e power 9 and Poisson ratio is 0.3. Just say OK. Just apply. Now we have to include the stress strain function. Here you just type it as traction. Here you can see there is an option called traction. Just edit. So automatically the sigma function will add here. Stress strain data. Just OK. Just apply. Here you see we have included this stress strain curve. Just OK. Now we have defined the material. Then we have to assign the material to the model. Just go to assign a material, mesh and model. Just edit everywhere. Just steel. Just say OK. Just apply and OK. Now I have assigned the materials to the model. Then we have to define a functions, load multiplication function as well as the time step to solve the nonlinear analysis. So first I'm going to define a load multiplication function. Just load into F. Here it has to be a time. coordinate, just go here. Time, x coordinate is the time, y coordinate is the function. When time is 0, the load has to be 0. When time is 1, the load is 1. It is increasing in this manner. Okay, just say okay. Just remaining things are not required. It will take linear automatic function. Just apply and okay. Now load multiplication function I have defined. Then we can define the time steps. Just go here, def list real, start with 0 time until 1, step length is 0.1. Just say okay, just apply and okay. Then time step method we have to define. Just method is the auto method, edit this one. Minimum pass, maximum pass we can set. Minimum iteration it can go 0.001, maximum it can go 0.1. Just say okay, just apply and okay. Now we have defined time period and load multiplication function. Then we can go for boundary conditions. So go to BC and loads, assign a mechanical load. First one is we have to fix it. Just edit. So we can go for blockage. So first I'm choosing the group of element. Just say okay. Here displacement. Say okay. Just apply and okay. This one is the first one. I just renaming this into BC. Then I'm just going to define a load. So just typing for force. So this one is the force phase. Just edit. Group of element is the force. Just say okay. I just want to apply the force in. This is z-axis, this is y-axis, then this is x-axis here you can see. In fx, variable. So here, just see the load value is 1 e per 5 and by the cross-sectional area because we have to apply it as a pressure only. So 1 e per 5 divided by 0.4036. 1, we can name it force. 1 e per 5 divided by 0.123436. Just close the bracket. So this is the pressure value for to apply the force of 1 e per 5. Just apply and close it. Just okay. Then you just apply and okay. Now I have applied the boundary conditions and load. Now we can go for defining the solver. So this is actually a material nonlinear. We have to choose a nonlinear solver. So static nonlinear. Here time stepping is the list dr. Just say okay. Loads, we have to define two value. First one is BC, say okay. Second one is load. 0 has to be multiplied with the load function. Just say okay. Then we have to define the hardening curve, hardening algorithm. So for that, just go to compartment, edit. So it will automatically apply to all if you have a single component. If you have a more number of components, we can choose by group of elements. Then here there is option called relation and deformation. Relation, you just choose it as Van Mises isometric traction curve. There are different hardening property. We are choosing isometric hardening. Then this is, you keep it as petit. There are different options are available. I'm just using petit. If you want to use Simomaito also, we can use it. So petit. Then you just say okay. Then nothing we need to change. Just apply and okay. Now I have defined the solver. Then we just want to calculate the stress and Van Mises stresses from the solver. Just go to post processing, calchamp. Here we can choose the directional stresses, sigma element and sigma node. Here we can choose equivalent element and equivalent node. So if you want to calculate force also, reaction force, everything we can choose. As of now I don't want. So material model, just apply. Here there is an option called naming it. I'm just using the same name. Just apply and OK. Now finally we have to save the output. Just go to output, set output results. Pictures, code Aster. So I'm just naming as result.rmad. This is the file format we wanted it to open in paraview. Then choose mesh file. Result is not the static nonlinear solver, it's a calc champ. Then here there is an option called tau champ, make it S. Just OK. MAD format, just apply and OK. Now I have created the complete setup to solve this material nonlinear problem with the strain hardening, isotropic hardening. Now we'll solve this case. Just go to history view. Before running this case, just save this document. Here we can allot some more memory. I'm just giving 4048. 5 seconds. Just click this plus button. Then click this run. If any error comes or divergence occurrence in any one of the time step, we have to change accordingly. Now it is started reading the command file. Second iteration is going. Here you can see the relative residues. 60% is completed. You can see the relative residue. Yes, it is completed 100%. Now it is doing saving the output results. Here you can see the graphs one by one. 100% is completed. This is the time step graph, iteration graph, absolute residue, like this you can see relative residue. Now just see the command file. This was the command file actually, message file. By opening this message file also we can check. So this is completed without any error. Now we can open the RMD file to do the post processing. Now I'm just saving this file. Just go to paraview. Just right click and open. Pictures, code Aster 71. Here our file name is result. Just open it. Just apply first. So this is our model. First we want to see the displacement, how it is behaving. Choose the X displacement. So first do the reading the data. Initially it will take some time to read. Second one also just read the data. Third one read the data. So now we just go to the first one. Yes. So this is the plot. So as we have applied the load, so this is getting deformed in this way. Just go to wrap by vector, just apply. Just do some. Yes. Yes. This is the way we are applying the load. It is getting elongating the x-axis. Now whatever the load we have applied, it is behaving the same way. Now we can check the stress, what stress we are getting. So stress is getting very high, that means the material is failing. Just go to von Mises. See, so it is getting the stress of just 4300 megapascal. So it is material is failing. So the minimum stress we are getting here. and remaining area completely is failing. That is because of the load is very high. Just go to directional stress also. Yes. Now we can plot this data also, how it is getting deforming. So for that, just go to filter. There is search option. Just type plot. Here there is an option called plot data over time. Just enter it. So we have to choose the nodes. Any node we can choose. I'm just choosing here. Just apply. So just go to the plot. Here, just scroll down here. So here the X array name has to be a strain, but we are not calculated the strain. So for that we have to calculate the strain. So first we can check it with the data, how displacement is behaving in x-axis with the time. So just scroll down here. Instead of this thing, we have to choose show maximum. Go to fit screen. When the load is 0, so it is applying the load like this gradually. This is the way deformation is occurring. Now what we can do, we can calculate the strain. From that we'll rerun the case again. Just go to code Aster. Here in calchamp. So to calculate the strain, you just go to here, deformation, EPSI, element and EPSI node. Yes, that's it. If you want to equivalent strain, if you want, you can go for criteria. Now I'm just taking total strain. Just apply and OK. Now we can save this. We'll delete the old data. Now we'll rerun the case again. %20 is completed. Yes. Now it is completed at 100%. Now file saving is doing. Yes. Now it is done without any error. Now we can open the same file using paraview. So this is my folder. Choose this file. Just say OK. Just apply. Right click and open. Just OK. Just apply. Here go to displacement. Yes, the same results only. We can read first all the data. Then you just go to strain, axis strain. So it is getting a strain of 2.8 meter. 2.8. The strain value is 2.8. The maximum strain value is 2.8. So similarly, we can set the color. If you want to change the color into blue to red, we can change it by using this option. Just apply and close. Now we can plot it. Just go here. So filter, search, plot data over a time. Just enter it. Now just choose the element here. Just apply. Yes. Now just go to the plot data over time. In x-axis array, we have to choose strain. So this one is the here there is an option called maximum strain. This one we have to choose. In y-axis, choose the 1 meter stress. This one. And just scroll down here. Go to show maximum. And fit screen. See, up to this it's behaving elastically, then it's behaving in this way. So this is our stress strain curve. It's going beyond that stress strain curve. So here you can see here the curve is nonlinear only. Then it is going linearly. Here you can see the little nonlinear. Whatever the way we specified the curve, the same way it will come. Then it is go for linear. That is the way we have defined. So in this tutorial, we have learned strain hardening with material nonlinearity. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.